All right, we're back on page 4 of notes 5 of Calc C. We're talking about, we started off talking about the integral test, and then we noticed this pattern that was happening with some type of series. And we found something called p-series, and p-series are of the form 1 over n to the p. N is the thing that changes, p is going to stay the same forever. So 1 over n to the p will converge if p is greater than 1. It will diverge if p is less than or equal to 1. Also, p has to be positive in that case. Which I always kind of leave out because I feel like if it's not positive, then it's not really of the form. But I guess technically you should say it anyway. But anyway, p-series you just like look at and you know if they converge or diverge. So they're just awesome. They're kind of like geometric, except you don't actually know the sum. You just know that it does converge. You don't exactly necessarily know what it converges to, but whatever. Add up a trillion terms and you'll see roughly what it converges to. So let's see if we can do this problem. So because they're so straightforward, they usually get mixed in with other types of problems, like based on the assumption that you can just like look at it and tell. So let's see, determine all values of p such that, so we have this thing, the sum from 1 to infinity of 1 over n to the 3p. So that's a p-series, but like a weird p-series because it's like a 3p series, but that's okay. That's not going to be an issue. So this is p-series. And then we have the quantity p plus 1 over 3 raised to the n. So this actually, because it's raised to the n, this is geometric. So for p-series to converge, I know that I need the p-series. How would I spell that? P-series. Okay, for a p-series to converge, I know that I need the exponent of n to be greater than 1. So in this particular problem, the exponent of n is 3p. I need 3p to be greater than 1. So I need p to be greater than 1/3. Okay, so if p is greater than 1/3, then this purple series that we have kind of, we already know will definitely converge. So for geometric, I need the absolute value of r, and r is p plus 1 over 3. I need the absolute value of r to be less than 1. If that's the case, it'll converge. So this is the absolute value of p plus 1 is less than 3. So I usually think of this as, you're at -1, you can go 3 in either direction. So if I go 3 this way, it'll take me to 2. If I go 3 this way, it takes me to -3. That's not true. It takes me to -4. Okay, so what do I need to be true? I need, well, let me write this. -4p2. So this is for our geometric series. So I need both of those to be true. And if you want, you could do it on a number line. So you'd have this, right? So like 1/3, and you need p to be greater than 1/3. So you're like here. And then you have your -4 and your 2, and you need to be in between those. So like here. So you can see that the region that you want is this, or you can just logic it out or whatever, I don't know. So therefore, we need 1/3 to be less than p to be less than 2. That's our final answer. If p is in between there, both of them are going to converge, which is kind of interesting, right? So you have to combine things that you know about different types of series. You have to be really flexible when you're thinking about exponents. Like it's called a p-series, but then you see 1 over n to the 3p. Still a p-series, just now we need 3p to be greater than 1. And you kind of go from there. One of my favorite things to do with p-series is to be able to tell if an improper integral converges without actually doing it. So here, for example, instead of this integral, I might consider this series. But for this series, I know that p is 3/5, which is less than 1. That's scary. Got people joining the Slack channel and it's making little noises. Less than 1. Therefore, it definitely diverges. It's divergent p-series. Therefore, the improper integral associated with it also diverges. It's a very cool use of p-series, I think. So like here, we could compare this to 2 to infinity, 1 over n to the 9th, where p is definitely 9, which is greater than 1, therefore converges. So you can just kind of like use it backwards, which I think is like a new superpower that you did not have before. And now, so I don't like, I'm always hesitant to even mention this because if you've never like confused the two things, you're just not going to. But p-series and geometric series kind of look alike to some people. It's that for geometric series, it's like your ratio is constant and then your exponent changes. Then for p-series, it's your exponent is constant and your base changes. So it's like you have this kind of like interchange there or whatever. So like just don't get confused by them. Usually it's just like you've thought about geometric so much that you can't possibly confuse it with a p-series, but like who knows? So let's see. Determine if these converge or diverge. These are all fast. Okay, so that's good. This is definitely geometric where r is 1/2, which is less than 1. Definitely converges. Not only does it converge, it converges to the first term over 1 minus the ratio. All right, this, rearrange it, make it look the way you want. So here, so p is 2 greater than 1. Convert, I'm trying to write converges, but it's not working. Well, I'm trying to write conv period, and that wasn't working. This is geometric. R is 1/3, which is less than 1. Therefore, it converges. Not only does it converge, but geometric, we can find the sum. So what you do for the sum here is you take this and plug it in here. So we get 3 to the 0 as our first term, which is 1 over 1 minus 1/3. And here, p is 4/3, which is greater than 1. So converges. Okay, so they all converge, so that's stupid. But that's fine, stupid, but fine. And here's a little summary of the tests that we know so far. So there's 5 of them. You really have to like keep on top of it. There's a lot of tests, but like they build and it's not that bad. But once you kind of like get out of the loop, suddenly it's overwhelming. So nth term test is the limit of the nth term 0. If it's not, diverges and you're done. If it is 0, you need to use one of the other tests. So, move on. Geometric always look the same. P-series always look the same. Integral test, can you integrate, right? If you can't find the integral, which is why it's a really good calculator test, it's harder to use by hand. But if you can integrate, it's a really good way to go. And then telescoping, like by definition, if it's telescoping, it converges pretty much. You just have to notice that it's telescoping, which means partial fractions sometimes. A lot to do. Also, you can find the sum of a telescoping series, which is unusual. So of the ones that we know, geometric and telescoping, you can find the sum. The other ones, you can tell if they converge or diverge, but like that's all it tells you. It doesn't tell you the sum. All right, so I will be back in the next video and we'll keep going. So see you there.